people hear me now? Okay, thank you. Good evening, everybody. So my name is Peter Weichman. The students in the Boulder School know me, but perhaps a lot of others you don't. I'm one of the organizers of this year's Boulder Summer School entitled Hydrodynamics Across Scales, which is sponsoring tonight's lecture, which will cover some intermediate set of scales, below galactic and above bacterial, perhaps. Ordinary Professor Leo Rajachowski of the physics department here would be here now introducing things, but he's unfortunately fortunately traveling. He's been a prime mover for this school since its inception in 2000. It's taken place every year except one during the pandemic, I guess, since then. And I was actually present for that first school, just sort of by accident. And I'm amazed and pleased that it's still going and has such a broad viewpoint to include this year's topic. So every July, 65 best and brightest are invited. PhD, advanced PhD and postdoctoral students are invited to attend 4 weeks, grueling weeks of lectures by nearly as talented expert speakers. Past topics have ranged from superconductivity to quantum information to biophysics, and of course this year's sort of multi-scale topic. The school is supported by NSF and the University of Colorado, and this lecture is a prime example of our efforts at broader public outreach and maybe a good use of your taxpayer dollars. So, today's speaker, Baylor Fox-Kemper, is a member of the Department of Earth, Environment, and Planetary Sciences at Brown University, working mostly within the climate and environmental group. He's also a fellow of the Institute at Brown for Environmental and Society, and collaborates with the Fluids at Brown program and the Brown Theoretical Physics Center. From 2007 to 2012, he was a fellow of the Cooperative Institute for Research in Environmental Sciences and an assistant professor somewhere within a block or two of here, I guess. Before Boulder, he worked with Raphael Ferrari at MIT and Jeff Ballas at Princeton in the Geophysical Fluid Dynamics Lab. His PhD is from MIT and the Woods Hole Oceanographic Institute, joint program on oceanography, working with Paolo Rizzoli and Joe Podlosky, whose textbook I'm actually familiar with, at least. Baylor is a lead author with Helene Hewitt of Chapter 9 of the most recent IPCC report, 2021, focusing on ocean, cryosphere, and sea level changes. And it's a topic, I guess, that you'll tell us about tonight. Thank you.
Thanks, everybody, for coming. All right, I'm getting a lot of distortion, so I'm going to take off my mask. Okay, so this is a talk that's going to touch on a bunch of different things. And, I'm now previously from Colorado, but now from Rhode Island. So I will talk about sea level, which is of less interest here maybe, but I'm going to try and link sea level to some of the things that you might care about here. And in the end, we'll come around to points that touch on the topic of this meeting. So what are the cross-scale interactions that actually end up accumulating in a meaningful way on the climate system? And how can we quantify the uncertainty that goes along with that if we can't directly represent those small-scale processes on their global impact? So, turn this down a little. Well, everybody can take a look at that picture. So what's wrong with that picture? Aside its slightly gory nature. So what's going on? Why are they different colors? Because they're different species. One of them is not supposed to be in the Arctic, but is in the Arctic. Yeah? Exactly. So a red fox is bigger than an Arctic fox and stronger and faster than an Arctic fox, but normally they don't overlap in their habitat. But they do if it gets warm enough for the red foxes to start heading more into the Arctic. So I didn't take that photo, obviously. That was a wildlife photograph of the year about 5 years ago. And it's because it simultaneously captures both a sort of dramatic wildlife moment, but also this aspect of climate change coming together in one photo. Oops. So here's an outline of the kind of things I'm going to talk about. And you'll start, maybe some of this will make a little bit more, but I'm going to start out, and this is actually apologies to those who heard my lecture earlier this morning. We'll see a little bit about why the oceans are vast and diverse and what that means. And we'll see some visuals that kind of give you a sense of some of the diversity as we go from the biggest scales on the Earth all the way down to the smallest scales that are still fluid dynamics like. And then I'm going to talk a little bit about what the IPCC is. And then I'll jump into the science of the IPCC, both our chapter, which is on the ocean, cryosphere, and sea level change, and the observed changes globally with other metrics as well. Trying to focus on the things that are, the best known pieces, not best known in terms of widely understood, maybe outside of a community of scientists, but the best known in terms of the things that we're most certain are well represented by the observations and the models that we have today. And then I'll jump a little bit into the effect of the unresolved scales, touching on the topic of this meeting that has brought us all here. And then in the end, I'm going to talk about some of the online repositories, and both, that's kind of a fun, you can go there yourself and find out what's coming kind of thing. But it's also, I'll talk a little bit about why I think that's an important part of the new IPCC report, which is a new development. And we're starting to see how these kind of old-fashioned concepts, the IPCC has been going for over 30 years now, how they're modernizing and delivering information around the world. Okay, so on the largest scales that we're going to think about, this is a simulation of the Earth's oceans and actually sea ice as well, although the sea ice you can't see in this picture. And what you can see, so this is coloring surface speed. It goes from about 1 meter a second down to 0. And you can see lots of different features in lots of different places. You can see pulsations that have to do with the weather, pulsations that have to do with the tides, and then kind of swirly things that are moving slower around the Earth. Those are ocean eddies and ocean currents. So here's the Gulf Stream, which most people have heard of. Here's the Cryosphere, which is a little bit less common. Here's the Antarctic Circumpolar Current, and all of the eddies that are attached from it and being shed away from it. This model is one of the finest resolution global models that was ever run when it was run a few years back. It's at 2 kilometers resolution all over the whole globe. And it has all of these detailed features. But actually, this model has only been run for about 2 years of simulation time. And the output from those 2 years is measured in hundreds of petabytes. So, bigger than most data centers around the world. That's an enormous, many hundreds, millions maybe of libraries of Congress worth of information. So why do we bother to do this? It's because we want to understand these smaller scales and maybe how they interact with the larger scales. But a typical climate model doesn't have these kind of features in it. A typical climate model might have a ocean resolution 50 times coarser. So it would have a 100 kilometer by 100 kilometer grid. And a lot of the interesting features you would see here would be not represented so crisply. And so we're going to try and think through this talk about what that does to climate models and what uncertainty that infers, but also just to kind of get a sense of the beauty of those kind of phenomena. If we go to the little blue box over here and zoom in to the South China Sea. Oh, and I forgot, one of those eddies, one of those big swirly eddies coming off the Gulf Stream is about the size of 1 to 9 Rhode Islands. So if you want to think in terms of how big it is, well, maybe in Colorado, Rhode Island seems like a very small place, but these eddies actually are even a partial fraction of Colorado sized. Okay, so here's the South China Sea, like I promised. And this is now, we're looking at temperature, surface temperature, rather than surface speed, but you see similar kinds of features. You see a lot of swirls. And actually up here on the shelf, the black lines are indicating where it gets shallow as you approach China over here. You can see that something is happening. It's switching over to waves, and those waves are propagating on shore. And there are all kinds of pulsating eddies over here that are leaking through this strait between those arc islands. If we want to go smaller, oh, I should have shown you the box. Here's the little box that's about this size. Now we zoom into a box of that size. We actually can't really do it in the same model. We've run out of resolution to have something interesting going on in the box. So we switch to another model that's just the same size as that box and keep continuing down. And in this model, I'm showing surface temperature again in the top, and then at mid depth, temperature looking from above, and then temperature looking from the side. And you can see looking from the side that there's something very special about this upper 50 meters or so. There's kind of a pulsation going on. That's a mixed layer that's mixed every night when it's cold, and then it is, bouncing up and down as the sun is turning on and off, as the days are coming and going. And that mixing is preserving a vertically well mixed layer here, where the temperature is pretty uniform. And that being uniform is part of what has to do with this upper layer of temperatures. You can also see those pulsations here now that you're looking for them, being different from the larger eddies below that. And so these smaller features are what we call the submesoscale. That's the next scale down, but we can zoom in still farther into this little box. This is another simulation focusing on the submesoscale scale. And you can see now the submesoscale eddies, those little tiny eddies, are now the big eddies in this domain. And there's another little box here. You can zoom into that. And now we just see one temperature front, from cold temperature on this side to warm temperature on this side. And this is a little bit unlike those other sea surface temperature diagrams I was showing you, that we're not showing sea surface temperature everywhere. We're only showing it where the vertical velocities are large. So we're looking at surface temperature just where the flow at the surface is coming together and going down. And so the shape of these little structures is telling us about the shape of the turbulence that's mixing that mixed layer. So we're resolving net another scale down. Now, you probably have lost track about how big we're talking. This box is 1 kilometer by 1 kilometer by 40 meters. So we went from the global scale at 2 kilometer resolution down to a model where this grid, there would have been 4 of these simulations for each grid in the first model we started at. But we can still go another scale down. Here's a little tiny box. And when we get down to that scale, we start to see things like the viscosity and diffusivity of the fluid itself mattering. So I suspect, people don't normally come to a lecture put on by a physics meeting unless they're a little interested in physics. People probably have thought about fluid dynamics, maybe viscosities and diffusivities and things like that. All of that stuff is important, but it's important down here at the bottom of that scale cascade. As we go back up to the global scale, where different phenomena, different shapes, there are different kinds of waves, there are all different kinds of things going on across the set of scales. All of that contributes in some way to what the oceans do when they're responding to climate change. So we have this very complicated fluid that's different on different scales. It does a lot of important things we're going to talk about in a minute to regulate the climate system, but it's also a very complex turbulent flow at the same time. Okay. So the oceans are vast, very, very big. We have all of those scales to zoom in on, and diverse. There's lots of different stuff happening on different scales. So we'd like to understand, what that means for the climate. So now to jump over to the other side, what's the United Nations IPCC AR6? Okay. So the IPCC is a panel that's convened by the United Nations to study climate change. And every 7 or 8 years, they release a report called an assessment report. This is the 6th assessment report that came out in 2021 and 2022. There are 3 different working groups. The working group I was in is the one that's about the physical climate, like how does the climate system work? But then there's a second one that's on how do we adapt to climate change? And then a third one that's about how can we reduce our emissions and maybe mitigate the effects of climate change. Those 3 working groups collaborate with each other. But I want to tell you just about the working group 1, because we're talking about the science side tonight. So that's what I want to focus on. So just that working group 1 is 234 authors from 65 countries. It's about a third women. 30% of them are new to the IPCC, including me. This was the first report that I had worked on. So how does this work? So we write a draft. We invite people to come and comment on that draft. And if you think you are an expert, you are invited to comment. So it is a self-determined expertise. So if you do the hard work of figuring out exactly when to sign up and where, you are welcome to go and do it. And actually, I got a classroom full of undergraduates to sign up on a previous report because they were reading that report as part of their homework. And I thought, if there's anybody who's going to say, this figure doesn't make sense, it's an undergraduate who doesn't understand that figure, which is exactly the kind of feedback they need in part. But also scientists from all around the world and almost all the governments in the world contribute to those reviews process as well. So we go through a cycle of multiple drafts, and then the final report is reviewed by the governments one last time, and then there's an approval session, which normally happens in a room much bigger than this room, where all of the governments, hundreds of governments come together, and you go through every sentence of at least the summary of the report. And so, whichever country raises their hand and says, I don't agree with that sentence, you have to change this word, but for this reason. And then they go to the scientists, and the scientists say, no, that's not the right word for this process. We have to use this word, all of this. But due to the pandemic, this all happened on Zoom. So if you'd like to imagine how that process went, I was sitting on my back porch at about 4 o'clock in the morning, trying not to wake up the neighbors and interacting with these governments all around the world on Zoom. So along with my colleagues from all over the world who we'd written this report with. That's why it takes 7 years, is because that process is, you don't want to do it more than once every 7 years. Yes. So in that, the IPCC doesn't do new science. They just review already existing peer-reviewed science. It's already been published. There's certain deadlines they had to have appeared by. So in this Working Group 1 report, we assessed over 14,000 publications. And then there were pushing 80,000 comments in those reviews. In our chapter alone, we had over 12,000 review comments. And all of the responses to the reviews are cataloged. So if you would like to go see what my authors and myself did to respond to our 12,000 reviews, you can. That's a public document. And it's meant to be that way so that everybody's getting a fair hearing, and you're really trying to make sure that you make this as scientifically accurate, but also as representative of the interests at play in this complicated process. Okay, so here are the authors from my team. Let me move this picture so you can see everyone. And as you would expect, so there are 3 of us who are the coordinating lead authors, myself, Helene, and Kundi from China. And then there are review editors who help us manage all those tens of thousands of review comments. And then these are the lead authors, are the rest of the folks. And so everybody here is an expert either on ocean, cryosphere, or sea level, or a combination of those. And that's the team that we put together. So it took a long time to figure out how to talk to each other. Normally oceanographers and glaciologists and statisticians don't talk to each other. So that was part of the process. In addition to this, we actually had 5 chapter scientists who were younger scientists, kind of grad student postdoc level, who helped us out with pieces of the story, plus 73 other contributing authors who gave us like a paragraph here or a particular data set, a particular figure. So about 100 authors just for our chapter. So there are 12 chapters and an appendix. All of the chapters have about this scope of work. And an atlas, not an appendix. Okay, so that's what the IPCC is. We don't do new science. We just assess the science, we bring it together, and then we try and tell the most straightforward, most accurate assessment of how certain that science is or uncertain that science is, what new developments have happened since the last report 7 or 8 years ago, what things have gotten more certain, what things have gotten less certain. There are examples of all of those. I'm happy to answer questions about those when we'll get to the end, which is of those different varieties. Okay, but so what does our chapter cover? Well, so there are parts of the report that are focused on kind of the big picture, like what's coming this century. And then there are parts of the report that are like, what are these small scale things that might or might not be important? The processes, those particular details that might contribute or might not contribute to some big scale metric. So our chapter is focused on the processes, and it's really the processes around sea level. So what are things that contribute to sea level? Well, sea level is really, it's when the volume of the ocean gets too big for the bucket that's in that, the basin that it's holding in, and then it rises. So you can make the ocean have a bigger volume by expanding it. That is, warming up the ocean expands, and so it overflows its bucket. Or you can melt ice on land and put that water into the ocean, making it more massive and also more voluminous. So either way, that's the way you get to sea level rise. And so we had to work both on that ocean expansion, the warming of the oceans, the changes of the currents that might affect the regional distribution of sea level, but also have other ocean-related impacts. Then the changes in the Greenland ice sheet, which if it were to all melt, represents about 7 meters of sea level equivalent. High mountain glaciers, which represent about 30 centimeters of sea level equivalent. And the Antarctic ice sheet, which represents about 58 meters of sea level equivalent if it were all to melt. Whether it melts or not is a very complicated process. So things like the ice shelves, which are these floating barriers around Antarctica, and the way that they buttress or interact with the ice sheet that's on land is the kind of process that the glaciologists were really interested in telling us what the latest science was about. We also think about things like the albedo of ice, particularly sea ice. So that's when, if sunlight comes in, if it's absorbed by the oceans, it warms the planet. If it's reflected because it hits sea ice instead, it doesn't warm the planet. So if the amount of sea ice is changing, this brightness of the Earth changes in response, and that affects the whole Earth's energy balance. And that's part of the story we needed to understand. But of course, it's not just processes. The vast majority of the Earth is covered with either ocean or cryosphere. There's, so here, very simply, the ice sheets in Antarctica and Greenland cover just over, and if I remember right, 12% of the surface of the Earth. Sea ice, this frozen or seasonally frozen area, is another about 10% of the Earth's surface. The oceans underneath and elsewhere are about 72% of the surface of the ocean. Then things like permafrost, small-scale glaciers on mountaintops are all parts of addition pieces of this story. And snow-covered regions, including where we are seasonally, is a snow-covered region, and so too is Canada and Russia. Okay, so, but before I get I always get excited about talking about the science of these pieces. I want to make sure that this is actually a pretty serious story at the same time. So this is the site. It's now called Ak. It used to be called Akjökull, and Jökull means glacier in Icelandic. And in Iceland, they catalog all of the glaciers because they're important resources for fresh water and just kind of interesting features. This is not a glacier anymore. It used to be a glacier. And in response, an Icelandic artist, Andrés Snær Magnusson, went up and put a plaque on it that said this: so Ak is the first Icelandic glacier to lose its status as a glacier. In the next 200 years, all our glaciers are expected to follow the same path. This monument is to acknowledge that we know what is happening and what needs to be done. Only you will know if we did it. And 2019 at 415 parts per million CO2. So we're quite a bit higher in CO2 and just a few years after that already. So places in the world are changing. Parts of the cryosphere, that is the frozen parts of the world, are changing in detectable ways right now. And we have a long way to go before we're through with that process. So next, I'm going to jump to what we observe changing now and what we'll observe in the near future as the projections and how human decisions affect the span of those projections, but also some of the uncertainties in those projections. Okay, so well, let me pause. Are there any questions at this moment before we jump into the sort of projections and science part? Yeah, of course we got some. Here we go.
I'm curious what the relative contribution of the thermal expansion compared to the melting ice is still rising, how the projections change.
Absolutely, that's a great question. The thermal expansion and the melting of glaciers have been the leading two causes over the 20th century, but now the melting in Antarctica and Greenland is catching up with them. And so thermal expansion will probably continue to be the largest single source, but the melting in the cryosphere is either the same size or bigger, depending on how much of the cryosphere you include. Like here, another question? Oh yeah. So it is a different part of the process. So in my own research, I mean, we like to be groundbreaking. We like to have crazy ideas and see them through and figure out whether they're important or not. This is a different process than that. But I have to say that the decision-making, aside from the page limit, which we barely snuck in at under 4,000 pages, but that was strictly limited chapter by chapter to get that to that modest size. Aside from throwing things out because just the page limit demanded it, there was a pretty reasonable scientific argument for why things were included. And most of that had to do with the fact that there were updates since the last report. So a lot of interesting science doesn't get mentioned because we already knew that in the last report, and there's not really a new update. But pretty much everything new that should be mentioned gets mentioned over that intervening years. The real part, the part that makes it a lot less frustrating is that everything comes with an uncertainty level. And so frequently things get included, but they get included at low confidence. And so maybe you might, oh no, that was medium confidence. That, I know those people, they were really good scientists. That occasionally got frustrating, or that definitely shouldn't be high confidence, that should be medium confidence. Those sort of things are hotly debated. But that's actually where the real meat of the science and the scientific assessment gets done, is deciding those confidence levels, which is, and that's not a frustrating process. That it was actually a surprisingly scientific and intense process of thinking about how to do that, whether we could get different lines of evidence. To have high confidence in something, you have to have multiple intersecting lines of evidence coming from different evidentiary bases, different groups using different instruments, and they all have to agree. And so sometimes when we had a low confidence measurement, we go look for other papers that might support it or might refute it. Or we would find, wow, there's a lot of papers on this topic, but they all disagree. So that's still not high confidence. And that process is where the real science gets done. But it's not the same thing as sort of, I had a cool idea and I ran a model and showed it. It has to be unanimous consensus the entire chapter. So all of the confidence levels in our chapter, in theory, everyone has either decided, I don't know enough about that to have an opinion, or if I do have an opinion, I agree with that assessment. Yeah, which, you could have an outlier that was resisting, but in practice, that doesn't happen very often, that you really, by manipulating the confidence in exactly what you're assessing, changing the sentence to make sure that the right caveats are in place, everybody ends up happy in the end with the level you get to. Yeah, question. Yes, we're going to talk about how fast and how much right now that we're coming to. Carbon sequestration affects the acidification of the oceans a lot, but not so much the heating of the oceans, well, depending on how you do it. Some of the carbon sequestrations rely on bringing very deep seawater up to the surface where it would absorb carbon. And in that process, you may actually end up taking up more heat because you're bringing cold water to the surface and letting it warm up. But not all carbon sequestrations. Kelp forests would not necessarily have an obvious heating of the ocean effect, even though they might end up sequestering carbon. There's one more question up here. Okay, all right. So let's talk about some figures. So the IPCC spends an awful lot of time working on figures. Many of the figures I'm going to show you went through hundreds of drafts before they get to this version, which is kind of an insane thing to think, but it's kind of fun, and they really are pretty in the end. So let's talk about these two. So this one on the left is maybe the most famous climate change figure. This is what's called the hockey stick. And at least in the first version, it was called the hockey stick. And it compares the temperature over a relatively recent, but by Earth's history level, but by human level, a long time. So back to the year 1, the last 2,000 years. This is all reconstructed from paleoclimate records, things like tree rings. And then when we get into the industrial era from the 1850 to present, we have observations, and it's actually superimposed on the continuing paleoclimate reconstruction. And it's called the hockey stick because it jumps up. And the present temperature is unprecedented and more than this whole record. There's nothing that looks like this on this record. There's nothing that jumps up like that, and there's nothing that gets that high. And in fact, you can actually use other paleoclimate proxies, which are not as detailed as this, to say that this is actually the warmest multi-century period in more than 100,000 years. So that goes back all the way through the last ice age and into the interglacial before that, before we start seeing temperatures as warm as where we're at today. So yeah, climate does change a lot, changes about this much normally. That's not normal. It's quite unprecedented. Well, you could say, okay, it's not our fault. That just happened, right? So this other figure on the right-hand side is the one that tells you how one of the cleanest ways that we know why it has to do with human activities. So here's the black line, which is the same black line. This is the global mean surface temperature, the record as observed since 1850. And then this kind of tan envelope is showing climate models that include human and also natural forcing of the climate system. So land use change, carbon dioxide, methane, aerosols, plus volcanoes, solar cycles, other natural variability, that goes into this tan envelope. And that range is the range of all the models. So from the models that were hottest at that moment, the ones that are coldest, and then the ones that are warming faster at the top or lower at the bottom. And you can see that the observations stay within that envelope pretty well. It's not quite equal to the mean, which is this line in there, but you wouldn't expect it to be because the mean is averaging over a lot of variability like El Nino and things like that, that the real record had in it. And then when we look down here at the green envelope, that's the same ensemble of the same models with the same physics, with nothing changed except removing the effects of human activities. So they take away the land use change, they take away the carbon dioxide emissions, they take away, and you can see that the observations break out of the green envelope back here somewhere around 1970 and stay out. So you would say the recent decades are inconsistent with no human activities as far as the global warming in this metric. Okay, so you put these two together and you can say human influence has warmed the climate at a rate that is unprecedented, at least the last 2,000 years. And you can say the change in global surface temperature, and I was going to say that there's an anthropogenic piece, which I haven't got on this slide, but I'll come to it in a second. Oh, human influence has warmed. Sorry, human influence has warmed. So it's both of those pieces. So human influence, okay, exactly which part of what we were doing did what. So this is a lot of technical stuff to figure out, how much comes from greenhouse gases and how much comes from aerosols and how much comes from solar variability and how much comes from internal variability. And so this little chart is showing you the different breakdowns. And if you were, a lawmaker, you might say, oh, look, there's the big red one. Whatever that is the thing I might make a law to address, and that's carbon dioxide, because that's the big one that's driving most of this. And then the other thing you might read off of this figure is when you take all of those contributors and you add them up, you get this. This is the total human impact on the climate system. And here's the observed change to the climate system. They're the same size. So to a first approximation, 100% of the climate change that we've seen is due to human activities. It's all us. So the observed warming is driven by emissions from human activities, with greenhouse gas warming partly masked by aerosol cooling. And you'll notice that neither that last statement about warming nor this statement have any of those certainty levels that I was talking about before. And the reason why is because they're so certain at this stage that the IPCC assesses them to be a scientific fact. These are not part of the conversation about how confident are we. We're just measuring exactly how accurately we can get those pieces of the story in place. This one is, this human influence part no longer being assessed is stronger than the previous report. Well, but my chapter was about sea level. There's also a hockey stick for sea level, and here it is. And here we do have just high confidence because we don't really know all the pieces, and we're comparing it to a paleo record that's a lot more wobbly than that one we were just looking at. So maybe it's not quite as unprecedented. But anyway, we're pretty sure that over the last 3,000 years, we haven't seen sea level rise this fast over any other century than we saw over the 20th century to present. And here are a bunch of numbers about sea level, which, and human influence is very likely. So very likely is another one of these keywords that has some sense of confidence in it. The main driver is in 71. Okay, so how do we get to that very likely? Well, we can think about all the things that contribute to sea level. Like we said, we could melt ice on land and we could put that water in the ocean, or we could expand the ocean by warming it up. And if we just estimate by measuring the ocean at the surface, at mid-depth and at the bottom, the change in the glaciers, the change in Greenland, the change in Antarctica, we add those all up and we get a pile of things like this. You also can, take land out of ponds on land and put it in the ocean, and that is the land water storage change. You add up those separate independent measurements of all the pieces of the story, and you compare them to the satellite observations of sea surface height, where you bounce a radar off of the surface of the ocean, and they add up to be, at least within error bars over here, the same measurement. So not only do we know why the sea level is rising from each of the different contributors, we know that there's not any big missing source that we're not monitoring right now, where they add up consistently to each other. We can do a better job by reducing the error bars on these, doing more detailed measurements, but we don't have a missing source of sea level rise. One of the interesting things, and I see John back there, is the sea level rise has a lot to do with the global energy inventory, because that warming of the ocean is actually where over 90% of the excess or anthropogenic energy ends up. It ends up warming the ocean. So you can do the same exercise with the same colors, breaking down where did the energy in the Earth system go. And now the story really is, wow, a lot of the energy went in the oceans, in expanding the oceans. Okay, so those are some of the observed changes. What about what's coming in the future? So this is maybe the most important figure for the future to think about. And this one is not as well known. It's actually only 2 IPCC reports old. That did not exist until then. And this is kind of a weird thing to read, but it's temperature on this axis, or warming level of the whole Earth, global surface temperature. And on this axis, it's the cumulative carbon dioxide emissions since 1850. So all of the carbon dioxide that's been emitted going back to the beginning of the Industrial Revolution. So that's a kind of hard thing to estimate, but we can estimate it. And here are the observations again in black. Here's a historical model in gray. They're tracking together. And then now we're looking into the future. And these different futures have different colors. They're the shared socioeconomic pathways. This is big one with the big numbers, means burn like crazy, all the fossil fuels we've got. This one means actually we've already missed the boat to get on this low of a, but this means throttle the emissions very dramatically in the very near term. And so if we don't emit a lot, this is by the year 2050 that we get over here, we don't actually put out much more CO2, we don't go far. But if we emit a whole lot, we go far by 2050. So I hope everybody's kind of oriented as to what this says. Now, the most obvious part of this graph is it's a straight line. And the fact that it's a straight line means you tell me what temperature you want to stay under, and I can tell you how much carbon you have left to emit before you reach it. You tell me where you're comfortable going on this axis, and I can tell you how far you're allowed to go on this axis. You could extract carbon from the atmosphere and try and go backwards. That's very hard, and we don't really have the technology to do that at large scale now, but that's something a lot of people are interested in doing. But this is sort of the fundamental piece. So when people say, we are trying to stay below 1.5 degrees C or below 2 degrees C, what they mean is we're trying to avoid emitting that amount of carbon to get us across the 1.5 or 2 level over here. Okay, so this now brings me to a part where I will take off all the IPCC labels. I'll give you a little bit of my personal take, which is about that figure. Okay, so who put it up there in the first place? We're not even talking about future emissions, we're talking about past emissions. So that's something that you can look up on the web. Carbon Brief is very good at doing this. So out of over about 2,500 gigatons of carbon, billions of tons of carbon dioxide, the United States wins or loses, whichever you like, producing about 20% of that total signal. China is coming in next, then Russia, then Brazil, and then European countries down here. But if you add all of them together into the EU, it's about the same size as the United States, just a little tiny bit smaller. Okay, that's one way to think about who's responsible. So this is literally who's responsible for the global warming we've seen so far, and country by country breakdown. Well, you could say, okay, we didn't know what we were doing. Shouldn't really pay attention until we got to 1988, when maybe we might have had a chance. So we could pay attention to who's emitting the most this year. So who's presently to blame? And China reaches the top of that chart up here. The US comes in second, and the US is kind of steadily churning away. And then other countries as we go down here. The EU is next after the US on that combination. But maybe it's not per country. Maybe you want to know per person. So is the typical American on the top of this list? Yes, the typical American is on the top of this list. So we're emitting more per person per year right now, but at least we're doing better. It's going down. Our nationwide emissions are holding steady, but our population is growing. And so we're actually are improving the intensity at which we're emitting, but we're not close to zero yet, or even necessarily heading towards zero. And the Russian Federation is not only right behind us, but it's increasing. So this is different ways to think about it. Another way you could think about it is which companies are responsible for those cumulative emissions or per year emissions. And so Saudi Aramco is up here at the top for the emissions in 2015, Gazprom in Russia, et cetera. As you go down, fossil fuel companies, BP's down here. Over half of the global industrial emissions since human-induced climate change was officially recognized, so 1988 to 2015, can be traced to just 25 corporations. So there are 25 corporations that are doing half of the industrial emissions. There's also transportation and personal emissions as well, but half is coming from only 25 companies. So that's another way to think about this problem. Now, I'm not saying that you may feel personally like I'm pointing at you. I just showed a picture pointing at you. I didn't actually point at you, but anyway, I don't think this is necessarily the right way to think about it, but I think it's part of the story that you should have in mind as you're going about what's going on here. And one of the big reasons why this is not necessarily the right thing is because when we feel guilty, we actually tend not to do anything about it. Because if it's our fault, maybe we just try and avoid doing things, which is not what we want to do. But it's part of the fact soup that this whole story is based in. Okay, so if we go back to the SSPs and we spread them out on a time series, this is maybe more what you might expect. So here's high emission scenarios on top, low emission scenarios on the bottom. And so this is typically interpreted as we have the choice to not end up here and end up down here. Like that's up to us. And so maybe that is a positive spin on that. Okay. And we can do the same thing for sea level. And this goes back to the question from over here, which is how was it broken down? These little pills, these little different colors show you the different contributors. So while you're looking at those, I'll question. This is probably bracketing the truth. The most likely is probably somewhere in this range, in between these two. Personal opinion on that front. The oil companies actually, they forecast what their productivity is going to be somewhere in between those scenarios. So if it's those 25 oil companies who are making the decisions for us, their decisions would put you in that range. They're not at the top level. They're somewhere in the middle. And we'll come to what the countries have agreed to in a second. Okay, and so there's one subtle difference. So this is sea level rise, and this is a meter right here. This is in centimeters, so that's 1 meter right there. Notice that the temperatures really split apart pretty fast. So you can start to see a big difference by even 2030 or so between the high emission scenarios and the low emission scenarios. When we go to sea level, there's really not a whole lot of difference at 2050. You only really start to see things spreading apart later, and that's because oceans are slow to respond. They're slow to warm. Ice in those big ice sheets is slow to respond. And in fact, if we zoom out to a deeper time perspective and we look forward to the projections for 2300, even at low emissions, we're expecting to see sea level rise potentially approaching 3 meters. And at high emissions, it's somewhere in the 2 to 7 meter range. And if something fancy happens in Antarctica, we can't rule out emissions up to 15 meters. And so 15 meters of sea level rise means that, there's not Florida anymore. I mean, that's an extraordinary change. We don't think that is likely, but it's something that we can't rule out. And this is something we can't rule out under the high emission scenario. So wouldn't you like to just not take that risk is one way of reading this. But even if we do a good job of reducing our emissions, we're still going to have sea level to contend with. It's going to be hard. 2 meters of sea level in Rhode Island would be a big problem. Many of our cities and communities would have to retreat to higher ground. Okay, and this is what it looks like when Providence floods. These are hurricane-induced events. And we actually have a hurricane barrier now. I've built after this big hurricane in 1954 that protects us from getting this. But the point I wanted to make is this is not slow and steady sea level rise. This is a single day where the water came and it was the storm, you know, the low pressure system of the storm and the winds and the tide all hit at the wrong time and we got these big events. So maybe the way to think about sea level rise isn't so much meter, but how much more likely are those flooding events? And so this map is showing by emissions level top to bottom in 2050 and 2100, the factor more likely a 1 in 100 year event is. So a 1 in 100 year flood is like one of those ones I just showed you. If you look at the lowest emission scenarios, there are lots of places that are still down in these colors. So it might be twice as likely, 3 times, something like that. If you look up here at the high emission scenarios, there's hardly any white ones. There are a lot of these dark blues. And if you look over here at 2100 under the high emissions, pretty much everything is dark blue. What that means is the 1 in 100 year flood comes annually or faster. So you don't live in a place that floods like a 100-year flood, like those pictures I just showed you, very long, if that happens every year. So even though the sea level rise underpinning that is only about 1 meter on average, what it ends up contributing to that extreme weather or extreme flood risk is bigger than that. Yeah. So hurricanes are a really interesting thing because we know that hurricanes in principle could be enhanced by climate change because they derive their energy from the warm water below them and the moist atmosphere below them. But actually they can also be interrupted by other changes that come from climate change. So it's a much more difficult problem to determine exactly what the changes in hurricanes will be. So I'll leave it at that. We continue to have that being, and El Nino is the same way. We're not really sure what El Nino will do. We think some of the remote impacts of El Nino might get stronger, but El Nino itself is a hard nut to crack for projections, and so is hurricanes. So this is a last piece about this sort of projection scale. This is what governments have agreed to do, and that's sort of an important thing to think about. So in 2010, we were just shooting off, just going up, going up for the sky. Since 2010, a lot of policies have been put in place all around the world. And so the current policies, these are things that are actually laws, have locked us down to what's forecast to get just under 3 degrees centigrade. Although notice it's still going up to present, and then it goes down in the future. But anyway, all right, maybe you can trust them. All the things that they pledged to do at the COP26 meeting, these big meetings that come after the IPCC reports and discuss what the policy changes, would get us down quite a bit lower. And there are different levels of whether they're conditional on what other countries do or not, or those kind of things that push you down towards this lower level. And then, but down here is where 1.5 is and 2. And those kind of extreme changes that we're talking about, some of those appear in between 1.5 and 2. So some pretty serious changes we would like to avoid. We would rather be underneath 2 degrees to be there, but we're not presently on track. Okay, so maybe you want to say, why is that? And you could say, oh, well, like, kids these days are just so angry about this and it doesn't make any sense because we haven't seen warming yet. Yeah. I'm sorry, no. Can you speak a little louder? Oh, yes. That's a really interesting question. These are the locations of tide gauges that have long records. So that was why they were done. And so it's actually, those locations are based on where we have statistics that can be confirmed with observations. That's part of it. But absolutely, yes, it would be much nicer if sometime in the age of colonialism, we had decided that we should actually be monitoring the whole world for the global temperature, and then we would be in a much better state. We've only realized that recently, but when you look at things that you're like trying to find a long record for, you're still imprinted by that historical legacy. So yes, but you can estimate those biases and see what they're like, because we do have models spanning the whole time range. And if you believe the models, you actually can estimate the biases. And so that's part of it. But this particular metric was built where the tide gauge locations are, particularly because it would be an accountable change that could be measured against records that we know are going forward in the same place. No, this one is just those particular locations. Okay, so you might say, why are the kids so angry? And so let's look at those same figures that we just looked at, but let's look at them in a slightly different lens. So our recent leaders over here, this pink span indicates their lifespan up to present. I'm not saying that that's when their life is going to end. They're still alive. And this yellow span over here is the lifespan of, if they were to live to the same age, Greta Thunberg, the climate activist on the top, and my son Miles, who's exactly the same age as Greta Thunberg. All of the catastrophic changes are in the yellow. They're not in the pink. So it's not a surprise that these folks feel differently than these folks about the importance of climate change. And if you ask, when are we going to have to do all this reduction of emissions and damage to our economy and all the things that you hear scare stories about, that's the same story too. We've just been increasing our emissions solidly during the lifetime of our leaders. And all of these drastic future emissions are to come in the lifetime of the youth of today, if we're going to avoid these problems. So I would say it is absolutely fair that they are angry, and it is absolutely fair that they have a different perspective than what our present leaders do. And I think this is something you should listen to, and rather than dismiss. Okay, and there's an academic study showing almost the same thing over here on the right. If you want, I can give you the link to that. Okay, so let's talk a little about unresolved scales in the minutes we have, and then I'll show you a little bit about these about the repository. So one way you could get at unresolved scales is you could compare those high resolution models that we showed at the beginning to low resolution models and just see if they differ. And this is sea surface temperature, which is just one of the many things that we compare. And this is the global mean sea surface temperature record running along like this. And back here we have historical models and some observations of the past, involve buckets off of ships and cool things like that. And then we have those projections coming out the right, and then we have the distant projections over here on the far right, and we have paleoclimate reconstructions over here on the left. So we're trying to get the whole scope, but in the recent past and into the near future, we have a high resolution model that runs from 1950 to 2050. It's the green envelope. And there are, in fact, 9 different models from 1950 to 2014 and 5 different models that go out to 2050. But you can't, if I didn't tell you that was the high resolution one, you wouldn't be able to tell the difference. So as far as sea surface temperature on the global mean, it doesn't do anything different. So those eddies and all that cool stuff, which are just parameterized rather than directly resolved in climate models, apparently as far as sea surface temperature goes, doesn't matter that much. But sea surface height variability is a totally different story. So this is part of how we decide whether sea level is going to be more damaging in one place or another, is how variable it is due to the ocean currents changing. This is what the observations look like from those radar satellites I told you about. And you can see a lot of the variability is near those big currents, the Cryosphere, the Gulf Stream, and the ACC. And this is what high resolution models do. Not perfect, but kind of the same colors, same locations, great. You could trust these models as a representation of this. And this is what the typical models that we use for climate change do. They're about an order of magnitude too little variability in terms of sea surface height variability. So when we talk about regional sea level and the variability that comes from this, we had better be sure that we understand that this is an underestimate. So this is one thing where high resolution really matters. And we wrote a paper about this recently, which has to do with changes in the ocean and whether they impact Antarctica. And I'm actually going to skip a little bit here because I think this is basically, we're not going to be able to do much better by just waiting for computers to get faster. They're not getting faster fast enough to solve this problem before we need to know the answer. And then because this is a physics talk, we got to talk about the Nobel Prize in Physics that was recently won by some climate modelers. And one of them is by this guy Hasselmann, Klaus Hasselmann. And it was largely for this simple idea that temperature change in the ocean might respond to random forcing from the atmosphere with some kind of factor that had to do with how deep that layer was that I was saying was well mixed with some restoring force. And this is a simple stochastic differential equation. And you can solve it and you see that the variability of the atmosphere, what the atmosphere is trying to do, actually doesn't result in fast response in the oceans. It results in these kind of slow meandering. So let me show you what that looks like graphically. This is a model where it has an atmosphere forcing the ocean, and the colors you're seeing are those exchanges of heat between the atmosphere and the ocean. The swirling pattern is the wind. So you see storm systems and all kinds of cool stuff. And the ocean is just kind of sitting there. And this is those teal colors are showing you the location of the Gulf Stream and some of its eddies. And the green color is showing you the depth of that little mixed layer. And the ocean looks like it's basically not doing anything, but if you look closely, it is actually still moving a little bit. But if we just speed up the time, the ocean is also a turbulent fluid, just operating on a very different time scale. And so what Hasselmann's insight was, the Nobel Prize winning insight was, is that the ocean will be slow to respond and will give you signals about things like the overall energizing of the Earth system, while the atmosphere will be varying quickly on top of it. And that connects together with other kinds of ideas that we might have about how the ocean works, like sinking in the north, and this is called the thermohaline circulation sometime, or the meridional overturning circulation. And I had a very brilliant student, Galen Hall, who put those pieces together into a simple story. And he took something very similar to the Hasselmann model, except it just has an upper layer and a lower layer, but they're just uniform over the whole world. So when you have energy in the upper ocean, it could either go back to the atmosphere or it could go to the deep ocean. And that's not a very interesting model in and of itself, but it's very interesting when you make it, you tune it so that it quantitatively predicts what climate models are doing. And then you can look at the diversity of climate models and how they represent that upper ocean mixing or other high resolution changes. And you can figure out which of the simple parameters in this simple model change in response to that. And you can figure out quantitatively how much the warming rate of the Earth depends on different small scale phenomena one at a time by putting that connection together. And so an economist took a look at this, and this is, obviously this study is still not published. We're still working our way through it. But his claim was that the present value, if you could have the uncertainty range for transient climate response, it would be worth $10.3 trillion in terms of decision making. If you could accomplish in time for things to be adjusted by 2020, all right, well, we missed that, but 9.7 trillion if we can get it in time for things to be adjusted by 2030. So that simple theory that Galen worked on gives us about a 20% reduction. So maybe it's only worth whatever, 40% of 9.7 trillion, but it's still a very valuable insight in linking those small scale phenomena and how they impact the rate of global warming itself and how all those pieces fit back together. All those complicated ocean physics can be wrapped up into a relatively simple estimate of uncertainty. Okay, so let's talk a little bit about the online repositories, and then maybe we'll have a few questions. So the cool thing about the online repositories, there's one that's, interactiveatlas.ipcc.ch, and you can go check things out. Like, what does the Earth look like at different warmings? And you can go down to the regional scale. Like if we go here to where we are in the West, that's how much climate warming we get under a high emission scenario, and it's broken down month by month. So January doesn't warm as much as August, September, October seem to warm a lot in the fall in our region. That's not true of other regions. 6 degrees C here on the top. This is a very strong warming scenario, so you have to be careful about which scenario you're looking at. And you can do the same thing for precipitation, which is kind of fun. And actually, here with the ski industry and everything, you'd like to have a lot of wintertime precipitation, which seems to actually be okay for the early winter. Not so great as we get into March and April, where it seems to be drier than normal, and then kind of normal in the other part of the seasons. So I encourage you to go and check this out. And if you're interested in sea level, you can go to the same thing. And here again are those tide locations all around the world. You can get maps of what the sea level rise looks like, which is what is here in the back. Or you can zoom in on a particular place that you might be interested. Woods Hole happens to be one of the tide gauges that's near Providence. And the one that's on the other side is Bridgeport, Connecticut. And so while they're pretty similar, so there's not anything special happening in between our region and between those two spots. But if those big changes that I talked about might be changing in Antarctica, things are being accelerated by all those ocean processes that we aren't representing right now. You should think about a slightly higher uncertainty level, and that looks like this one, where you're now talking about potentially 5 meters of sea level by 2150. So, thank you all. That's the point. Over here first. Yes. Yeah, so all of these pieces are kind of linked together. I mean, the Earth system is driven by the sun, and the energy emissions back to space, and the weather are part of that cycle. So when the way that the excess energy near the equator makes its way toward the poles has everything to do with storminess and ocean currents and all of those pieces working together. And so extreme weather is sort of an extension to those processes changing. So when you move the mean a little, the extremes that attach to that can be pushed so that very unlikely events become tens or hundreds of times or thousands of times more likely, like we saw for sea level. So it's essentially, if you imagine a distribution of probabilities and you're shifting the mean a little, over here, you don't move far, but you move quite a bit in the vertical, because you may be on a steep part of that ascent. And so some events that are presently rare become much less rare when you shift over that probability distribution. And it's those shifts that tend to happen with, even with modest warming to a lot of the weather systems that we're seeing changes in. And then other things like wildfires, it's not hard to think if the Earth is warmer, if the Earth is drier, and the predictions are from drier in some places, like we just saw, it varies place by place. If it's warmer and drier, it's going to be more likely to burn. I mean, that's not a whole lot of crazy science to get you to that level. And also, if it's hotter, it's going to be more likely to have heat waves. That's also not so crazy to put together. The storminess, and particularly things like hurricanes, which are extremely complex phenomena on their own, are much harder to figure out the probabilities are. So that's where these higher and higher resolution models hopefully will help us. It also changes its shape, but the shifting part is easier to think about. We don't really understand what would constrain the changes in shape that well without having something like a really better model than we have right now. Question over here. Some will and some won't. No, so heat waves will get more likely, cold snaps will get less likely. So those pieces are pretty straightforward, but the size of the event and the persistence of the event is a much more complicated effect that has to do with the local weather patterns and things like blocking events. So the way that the jet stream meanders and the way that it sometimes gets locked into a pattern, which might be a prolonged Arctic, what do we call it, an Arctic polar vortex event, an Arctic blast, or all these things. That's because of variations in that kind of weather pattern. And some of them are likely to some of them have a tendency to get stuck. And so what the assessment is from the climate change perspective is whether they tend to get stuck more often or less often. And that's really a region by region and process by process assessment. So the ones that are really could cause a lot of damage, like hurricanes, receive an enormous amount of attention. But in that case, we actually aren't too sure what the net outcome is. Will we have more? Will we have fewer? Will we have stronger? Will we have weaker? Will we have, ones that go in a different direction, but they're the same strength? I mean, all of those pieces are on the table. So that is not a very easy thing to say, and certainly not to say about all of the weather changes globally. But things like the heat dome that happened in the Pacific Northwest, my understanding is that phenomenon was so unlikely that it just doesn't occur without climate change. Whereas with climate change, it still was maybe a 1 in many 100-year event, but we got it. So it went from sort of infinitesimally small probability to this might happen from time to time. And, you know, that's a problem. I mean, you know, like when you're thinking about how you respond to the earth and what it throws at you, we get used to a lot. We actually are pretty good at adapting. But what's challenging is when the things that we've already figured out how to adapt to and they're no longer a problem for us change into something else that now is a new problem that we don't have solutions for. So if you have high temperatures like they do in the UK this week, for the first time ever, they have a heat warning. They don't have, you know, air-conditioned rec centers like we do here, because when it's high temperatures, we've already built that infrastructure to protect people from those high conditions. So those kind of changes are really problematic for the response. And so hopefully, you know, the reason why I work in this field, the reason why I keep working on these models, even though the basic story of this climate change really hasn't changed since the first, well, maybe not the first, the third IPCC report had pretty much all the big top line ideas the same, were already there. The reason why is because I think better models will make us better able to adapt smartly in advance of these changes arriving more often than not. You know, maybe we still don't see the heat dome coming, but we might see increase in heat waves coming. And that's something we can get ready for and save lives and basically have it be less of a nuisance. Another question? Oh, way back there. Yeah. Right. So one of the reasons why I'm talking about those pieces is those are the more and the large scale phenomena more than the regional scale, is particularly because those are the more certain aspects of what the change looks like. But the thing that I didn't mention about that atlas, in the United States, at least, there's something called the National Climate Assessment, which comes out every 4 years. And it downscales these changes into the region you're interested in. And so state by state, they tell you what you need to be worried about. And they tell you which things are the most risky and which things are the hardest, are you well prepared for or not well prepared for. And that's one of the benefits of living in an affluent country, is that we can handle those kind of things. And we actually get the downscaling from our knowledge industry, like, you know, a lot of which is here in Boulder. In other countries, they don't have any information on a country by country basis. And so one of the really kind of revolutionary things about that atlas is that it's providing pretty good information on a regional scale for regions that have never had regionally downscaled information before, or at least not in an accessible internet ready way. And so I personally hope that, you know, our tech industry in the US and our universities see that kind of example and start providing more and more transparent, traceable, reliable information that downscales to places that can't afford to do it for themselves. Was there a question over here? Yeah, so I mean, that's where it comes back to this, you know, that straight line figure is, you know, how do you get on that straight line? How do you do something that keeps you from getting to the higher levels? And so incremental changes can actually, oops, now I'm stuck here. And I'm getting the spinning wheel of death. It doesn't want to let us off the hook. Okay, here we go. Let's go backwards. There we go. So incremental changes might slow the rate at which we go to the right-hand side. And so you can imagine, you know, if everybody in the world reduced their carbon footprint by 10%, that would move this a detectable amount. Actually, if just every American reduced their carbon footprint by 10%, it would move it by close to the same amount, because Americans are putting out a lot of the carbon, as we just saw. But realistically, can we do big changes like this? You know, this line is chugging along, going from 1850 over here, and it's actually accelerating the rate at which it's moving that way because our emissions are going up year by year by year. Slowing down that global fossil fuel-based economic chain is pretty hard to do. So it's hard to imagine that we can do it incrementally. It's hard to imagine that individuals acting on their own can do much, but individuals working together can do a lot. Individuals working together and influencing their government can do a very large amount, especially in countries like the United States, which has a very large share of the carbon emissions. So it's not impossible, but it is a big effort that we need to do to get all the way to net zero or beyond, to where we're actually reversing the direction of going from left to right on this bottom axis. Yeah. Yes. Yes, so I can a little bit. So this is a random atmosphere, and in this toy model, they were taking, this is a white noise signal. And what you get out of the ocean temperature response is a red noise response. Or if you put a periodic storm every week or whatever, however you want, a periodic forcing or day-night even, the ocean response will be on a different time scale. That's what this figure over here shows. So these are the frequency of the different constituents of the noise along this axis. And then the ocean response, oops, let me move this out of the way. So the ocean response down here it's rolling off depending on how much this restoring piece is. So you end up having less energy than if you just let it respond, but all of these slopes are tipped, which means that you get a more low frequency response than high frequency response. Whereas the atmosphere, if I were to put it on the same graph, would just be a straight line across. So the high frequency is suppressed by the ocean being hard to warm up, and the low frequencies can be suppressed if you have this restoring effect, which you might think of the restoring effect as being the emission of warm anomalies making more thermal radiation that goes back out to space. That would have an approximate form like this, or the fact that anomalously warm oceans might warm the atmosphere above. That would also have an approximate form like this. This is white noise in time in this particular one, but actually you could have another one of these at every point in space and have them all, they could have statistics. In this equation you do, for sure, but this equation gives you that sense between this model response and this model response. And this now is including both the time and space statistics and keeping the whole story together. The reason why this equation is a Nobel Prize winning one is because it's so simple, but it gets so much of the answer right. Yeah, back there. Yes, so there's a lot of, in the working group one, we spent a lot of time trying to estimate or talk about tipping points and find whether there were justifications for things like the Amazon forest might die back all at once, or you might lose all the coral reef in the world if ocean acidification gets too high. So yes, there isn't a lot of attempts to try and understand those processes, whether those regional changes then feed back onto the global in another way is thought to not be very important, with a few small exceptions. Things like if you melted all the permafrost fast and you released all the carbon in it, that might actually have so much carbon release that it would accelerate the rate of warming for a while. But even that was assessed as being not very likely to happen, at least in the upcoming century. So yes, there are these kind of like crazy things that could potentially happen, but we don't have a good sense that like one of them is definitely going to happen like next week. You would have heard about that. That would have been a bigger news story than the release of this report was. Oh, sure. Oh, well, I think I'm very optimistic in the adaptability of humans and the adaptability of ecosystems. If we can, particularly if we can help them along with good conservation measures. I'm not so optimistic that we're going to get off of that carbon emissions train and push ourselves down to those lower promise levels even. So I think when I think about optimism, it's more we can respond effectively and equitably, bringing everybody along to the extent that we can to these changes that are going to come, rather than getting off of this process by reducing our emissions immediately and really fast. And I would also say I'm not totally confident that we could reduce emissions really, really fast without compromises in like the way that our governments work and democracy and things in order to get that done. So I think, you know, we have a lot of pieces that are difficult nuts in reducing our emissions, but I do have a lot of faith and optimism in our ability to adapt. And I have a lot of faith and optimism in some of the technologies that will make this maybe not so bad. Things like solar power, wind power, especially safe nuclear, you know, like a lot of these things can really help take the edge off of what's coming. There's one more question over here and then we'll quit. Yeah, so there are lots of estimates of how much it would cost to do it with present technology, and it's unimaginably large. And there are also estimates of things like, what if we wanted to reverse sea level by pumping the water out of the ocean back on top of Antarctica and letting it refreeze? You can do this stuff. You can make these estimates. That second one would require 120,000 windmills to be installed in Antarctica to provide the power to put it up. The scope, the Earth is really, really big. The piece that I wanted to make at the beginning, it's very, very hard to reverse the changes that are happening in the Earth. And there's a big efficiency factor. So when, you know, tons of ice are melted by relatively small amounts of greenhouse gas emissions, that scale up factor is part of the way the Earth works. It's hard to break that with things as paltry as our human economic plans. It is a lot easier, even though it is extremely hard, to avoid those emissions in the first place. Yeah, thanks everybody. Thank you for coming. Great questions.